I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 20. Find the sum of the digits in the number 100 factorial. There's nothing super controversial here, and we've actually already done each piece of this puzzle before. We've written a ton of factorial functions, and we've summed the digits of a number several times. The only major point of note is that 100 factorial is a big number. The resulting number has over 100 digits, so we're going to need big nums. Let's write a basic draft in Python. Python has support for big nums out of the box, so the magnitude of the result won't be a problem. We'll write the factorial function first. The factorial of a number n is the product of all integers from 1 up to n inclusive, so we write a simple for loop to accumulate this product. For the sum digits function, we iterate as long as the input value is non-zero. At each loop iteration, we add the last digit to the total and divide the value by 10, truncating decimals to chop off the last digit. Note that Python's rules for conditionals treat values that are, in some sense, empty as false, while all other values are treated as true. So in the case of numbers, 0 is the only false value. In the case of strings, the empty string is false. Likewise, the empty list, the empty dictionary, and the special built-in constant none are all false. In our case, our loop runs until the input value is false, or 0. Finally, our main program is extremely simple. We take the factorial, sum the digits, and print the result. And that's our whole program. Let's clean it up a bit. The language we'll introduce in a moment actually compiles to Python, so the bits of code we've written here are, at least semantically, pretty similar to the domain we'll be working in later. Our factorial function is an example of a fold operation. In Python, the fold function is called reduce, and it resides in the functools module, so we can shorten our factorial function drastically like so. This reads as, take all of the integers from 2 up to n inclusive, then, starting at 1, multiply each integer into the total. Our sum digits function isn't quite as straightforward to translate. We could do some recursive trickery to make this look more functional, but in this case, the current implementation is probably the most readable, in Python at least. This is basically the code we're going to write. We're almost ready to talk about the language of the week, but first we need to take a brief tangent. Let's discuss mathematical notation. Mathematicians love to define operators, and we seem to relish coming up with ever more obscure notations sometimes. We have the basic ones everyone knows about, like a plus sign for addition, minus sign for subtraction, a small centered x for multiplication, and that funny line with dots above and below it that we use for division sometimes. You'll sometimes see the caret written as a sort of up arrow without the tail, used to represent exponentiation, in contexts where writing a subscript is infeasible. There's also more exotic operators. A circled plus is commonly used to indicate the categorical direct sum, and is uncommonly used to represent the exclusive OR operator. A circled multiplication sign is often used to represent a tensor product or a categorical monoid operation. We also have several relational operators unique to set theory. Instead of less than and greater than signs, when we're talking about subsets, we write a sort of rounded version of the usual comparison operators to represent the subset of and superset of relationships. That's not even getting into the more exotic and specific operators. Knuth up arrow notation uses multiple subsequent up arrows to indicate operations higher than exponentiation. That is, a single arrow represents exponentiation, a double arrow represents repeated exponentiation, the operation commonly called tetration, a triple arrow represents repeated tetration, and so on. All of these infix operators have a fundamental limitation, though. When we use them in a sequence, it's ambiguous which operator should be evaluated first. Does 3 plus 2 times 10 mean do 3 plus 2, then multiply by 10? Or does it mean do 3 plus the product of 2 and 10? To solve this problem, we artificially introduce an order of operations. We just mechanically say, as a rule, that multiplication happens before addition. If we want to circumvent that and actually do intend that the addition happens first, we have to write parentheses to clarify our intent. But this isn't the only way we can write an arithmetic expression. In reverse Polish notation, we write the two operands first, followed by their operation. Our original unparenthesized expression looks like this. This reads, take 3, take 2 and 10 and multiply them, then add the 3 from a moment ago. Our parenthesized form is written like so. This reads, take 3 and 2, add them, and then multiply the sum by 10. You might be thinking this looks less readable than the original expressions, though I'd argue that's less a fundamental truth, and more a consequence of the fact we're all trained to parse infix notation, and generally aren't taught reverse Polish notation until college, if at all. Now, if you're thinking this notation actually looks sort of familiar, you're right about that. Every stack-based language we've used so far, such as CJAM and GolfScript, has implicitly used reverse Polish notation, and evaluating this notation can be done with a stack. Take another look at our first expression here. If we want to evaluate this in a basic machine, we can start at the left. We see a 3, so we push a 3 onto the stack. Then we see a 2 and push it. Next, we see a 10 and push it as well. Then we encounter the multiplication sign. We pop two values, multiply them, and push the result onto the stack. Finally, we see a plus sign. So we pop the top two values, add them, and push the result. At the end, there's one value on the stack, and it's our answer. There's something else I'd like to draw your attention to here. Unlike our infix notation, reverse Polish notation never actually requires parentheses. Assuming every operator has a fixed arity, this notation can always unambiguously identify which order to perform the operations in. We can also do just the opposite. Rather than reverse Polish notation, if we place the operators in front of their arguments, we get Polish or prefix notation. Prefix notation has the same benefit as reverse Polish notation. Assuming all arguments have a fixed arity, parentheses are never required. Rebol is a programming language from the late 90s that used this fixed arity concept to its fullest. This is an example from the official Rebol 3 tutorial. This will print out the string example when run. It's equivalent to this more explicit form. But Rebol can infer where the parentheses go, because it knows that print and length always take one argument, and join always takes two. Suppose we instead swap the order of the length and join calls. What do you think this Rebol program would print? Think about it for a moment. Remember that join takes two arguments, while length and print take one each. If we wrote the parentheses explicitly, we would get this. We take the length of exam, which is 4, and then prepend that onto the PLE string with join. Then we print the result. In the end, we get forple. Rebol can parse this unambiguously because it knows how many arguments each function takes. It knows that length takes one argument, so it can take the exam, but not the PLE string. Join, on the other hand, takes two arguments, so it takes the result of length and the PLE string. Finally, print requires one argument, so it gets the result of join. By simply having every function eagerly take the arguments it needs, everything just works out. Now, we won't be using Rebol to write our full solution today. I promised a language that compiles to Python, and here it is. This is Pyth. Well, I don't actually know how to say the name, and unlike Osable, there's no pronunciation guide on Isolangs, so I'm going to keep pronouncing it Pyth. Pyth is a golfing language which compiles to Python, hence why its name is a shortening of the word Python. And Pyth makes extensive use of prefix notation in order to avoid explicit parentheses. All of the usual arithmetic operators are written in prefix and take two arguments. That includes plus for addition, minus for subtraction, star for multiplication, slash for integer division, and the percent sign for modulo. Spaces are optional in Pyth unless required to separate numerical tokens. So we can omit the space between plus and 1 here, but we can't omit the space between the 1s because then the parser would see an 11 as opposed to two separate 1s. Assignment is also done in prefix. We write the equal sign, followed by the variable name, and then the expression to evaluate for assignment purposes. All variable names in Pyth are one letter. Pyth is a golfing language, so in addition to keeping all of the functions and variables down to one letter, the language also provides us with a lot of built-in functions. Many of these come from Python and are merely shortened versions of functions that already exist. For instance, the s function takes one sequence argument and returns its sum, just like the built-in sum function in ordinary Python. The closing brace function takes an element and a sequence and returns true if the element is in the sequence, just like the infix in operator in Python. Some of the built-ins are more exotic. Prime factorization is done with capital P, for instance. And the chop function, written as lowercase c, takes a sequence and an integer and chops the sequence into n equal pieces, where n is the integer argument. That being said, not everything in Pyth is of fixed arity. Some functions have unbounded arity, which means they eagerly absorb as many arguments as they can. Take the open bracket function. This is the list constructor. It takes as many arguments as it possibly can, and returns a list containing those arguments. The argument list will extend until the end of the program, but it can be closed early with a closing parenthesis. Note carefully, we aren't closing these unbounded functions with a matching delimiter. Every unbounded function list is closed with the same delimiter, a closing parenthesis. If we want to close all open argument lists simultaneously, the semicolon acts as a sort of magical as many closing parentheses as it takes operator. When I said Pyth is based around prefix operators, I wasn't kidding. The language is really committed to that bit. Even control flow is simply performed using prefix functions that don't evaluate their arguments in advance. If statements can be written using the capital I function, which takes an unbounded list argument. Capital I treats its first argument as the conditional and, if it's true, evaluates all of its others in order. And since Pyth compiles to Python, its definition of true matches that of Python. So 0, empty string, the empty list, and the empty dictionary are considered false, while non-empty values are considered true. While loops are just the capital W operator, which likewise takes an unbounded argument list and treats its first argument as the conditional. Either of these constructs can take an else clause. Else is written as dot question mark and must immediately follow an if or while. Else takes an unbounded argument list. When it follows an if, it's the branch that gets executed on a false conditional. If it follows a while, then it gets executed when the loop finishes executing due to a false conditional, but not due to a break or exception. By the way, this particular while loop behavior isn't unique to Pyth. It's also true of base Python. One of the little-known features of Python is that a while block can have an else branch. The else branch evaluates once when the while condition becomes false, but it gets skipped over if a break statement exits the loop, or an exception unwinds the stack beyond the loop. The one other piece of the puzzle we need is reduce. In Pyth, functions like reduce, which take other functions as arguments, automatically wrap the appropriate arguments in a lambda statement. Here, we called reduce with a lambda as its first argument, which is by far the most common way to call reduce. Pyth assumes this by default. In Pyth, the reduce function is written as a lowercase u. It takes 3 arguments, and its first argument is implicitly assumed to be a lambda with argument variables named capital G and capital H. So if we want to take a product in our implied lambda, we simply write star GH, and the reduce machinery implicitly wraps this in a lambda for us. And that's the last piece of the puzzle we'll need. We're ready to write our program. Let's alter our Python program just a bit to get rid of the custom functions and do everything in main. Nothing too exciting, just a minor refactor, and our program is down to a crisp 10 lines. Now let's do it in Pyth. First, we initialize our helper variable k, which will be used to sum the digits in a moment. We set it to the value 0, which we write here as the capital letter Z. We could have used a literal 0 here, but Pyth supplies us with several pre-initialized variables with useful values, one of which is the capital Z, defined to have the value 0. So we might as well use it. Next, we initialize the variable d, which will be set to the factorial of the number 100. We'll calculate the factorial in one big reduce call, just like in Python. Lowercase u is the reduce function in Pyth. It takes 3 arguments, and the first gets the implicit lambda treatment. The lambda function we want to apply is the function which multiplies its 2 arguments, so we write star GH. Remember that the implicit lambda to reduce takes capital G and capital H as arguments. The sequence we want to iterate over is the range of numbers from 2, inclusive, up to 101 exclusive. Lowercase r is the range function in Pyth. Finally, our starting argument for the reduction is the number 1, the identity of the product operation. Note that we have to separate these numeric literals with spaces, whereas none of the other operators require spaces between them. At this point, the variable d contains our factorial, and the variable k will eventually contain our answer, but at the moment, it's initialized to the constant 0. We start a while loop with capital W. The while loop will run as long as our factorial, lowercase d, is greater than 0. Recall that the capital Z variable contains the constant 0. Inside our while loop, we set k, our accumulator value, equal to the sum of itself and d modulo 10. The lowercase e function is actually called end. It takes one argument, a sequence, and returns its final element. However, like many golfing languages, Pyth overloads its base instruction set to do different unrelated tasks on different types. So when we apply lowercase e, the sequence end function, to an integer, it takes the integer modulo 10. Having done that, we divide our factorial d by 10. Division in Pyth is always integer division, so we don't have to do anything special to truncate the result. Capital T is another one of those constants Pyth gives us by default, like capital Z. Capital T, of course, is defined to be the number 10. This ends our while loop. We terminate an unbounded parameter list, like a while loop, with a closing parenthesis. At this point in the program, d is 0, since our while condition was false, and k is our answer. At last, we print out the answer using the lowercase p function. And that's the whole program. All in all, we didn't use any optional whitespace, so this 35-character program is as short as it can be without revising some instructions. This gets us a correct answer and solves Project Euler problem number 20 in Pyth. Tune in next time when we take a look at problem number 21 in APL, the array-based programming language that inspired J.